श्वेतपद्मासना या ब्रह्माच्युतशङ्करप्रभृतिभिः देवैः सदा वन्दिता सा मां पातु सरस्वती भगवती निःशेषजाड्यापहा.
Thank you. Welcoming the guest is a part of code of conduct for the Indian culture. I request our technical team to present virtual bouquet on behalf of Honorable Chancellor Shri Purushottam Dasji Pasari and Vice Chancellor SVV Dr. Upinder Dhar sir to our Chief Guest Padma Shri Dr. Rohini Godbole ma'am. A warm welcome to ma'am. Thank you. Now I request our Honorable Vice Chancellor Shri Vaishnav Vidyapit Vishwavidyalaya Dr. Upinder Dhar sir to welcome our guests by his warm words and gesture. Hand over to sir.
Good morning. Our chief guest on this occasion, Madam Dr. Rohini M. Godbole ji, Chancellor, Honorable Chancellor of the University, Shri Purushottam Dasji Pasari, Honorary Secretary of the Trust, Shri Buradia ji, all faculty colleagues, guests, and my dear students. Today, we are celebrating a very special day. So, the Science Day is normally celebrated on Sunday, on 28th of February. But this year, Sunday being 28th being on the Sunday, we have organized this special session today itself. We are very happy that we have one of the leading scientists of the country with us today, Madam Godbole ji, who happens to be the first Indian woman scientist conferred with Padma Shri. Madam, our university is a very young institution. It was established by state legislation in 2015. And the question that was in our mind at that time was that how to make this institution different from all other institutions which are around. Therefore, we spent quite some time on this question that how to deal with it. We didn't want to be just another institution in the state or in the country. So we identified certain features which should be typical of our institution. Though our university is young, only 6 years old, legacy is very long. Our parent trust was established in 1884. So with this legacy, we wanted to give something different to the society and to the country. First priority, which has always been, was the quality of education. No compromise on the quality. This we made the resolve right from the day one. Number two, though we inherited the engineering college that was established in 1995, which had all programs accredited by the National Board of Accreditation, we thought that only continuing with single discipline is not different. Is not going to make any value addition. As a university, as we know, we have to be an institution offering undergraduate, postgraduate, and doctoral studies in multiple disciplines. So right from day one, we added new disciplines to our engineering discipline, like management, forensic science, social sciences, biotechnology, agriculture, architecture, and so on. And today we have 15 disciplines. Number two, we also believed that a university cannot function in isolation. The days are gone when would continue or function as a closed set. Therefore, we, right from the beginning, approached leading companies, that is industry, for integration. We signed MOUs with IBM, Red Hat, TCS, Impetus for the period of time to offer various programs in partnership with industry. Here the partnership means that one course is taught by industry executives every semester. So one course is the responsibility of the industry. So we jointly design the syllabus for such courses, and after development of such courses, designing and development of such courses, these courses are delivered by people from IBM, TCS, and other companies. So the intention was to integrate. Further on, we ensure that we have equal number of experts on various boards, equal in terms of academic experts and industry executives. So on each board of study, there are, right from the beginning, there are experts from industry as well as experts from academia. So they together work on designing and developing the courses which should be taught. Because ultimately, it is the future recruiter who can tell us that what will be the need of industry tomorrow. Student who is enrolled for BTech program, what kinds of jobs should be able when such a student completes 4 years? So the best people who can tell us are the people from industry, the recruiters. That's why we have representation of industry and also scientists on various boards. On one hand, there are people from industry. At the same time, we have people from R&D organizations also. For example, RRCAT, and also from Indian Institute of Science, Bangalore, from where Madam Godbole comes. Another feature that wanted to focus right from the beginning was holistic development of the students. As they develop holistically into reality, unless there is wholesome development of students, perhaps we may not be doing our duty well. Therefore, we promoted the activities beyond classroom, so that students go beyond classroom and develop the skills of planning, organizing, and networking, which has been happening continuously. Therefore, in other words, we promoted this university as a value-based, activity-driven institution. Values are in our blood, because as I said, 137 years back, when this the original trust was established, it was 100% a charitable institution, and it continued to be a charitable institution. Therefore, in our university, right from day one, we made 2 courses compulsory for all, irrespective of the discipline in which a student was enrolled. A student may be enrolled in engineering or management or computer applications or biotechnology, maybe humanities, social sciences, whichever. But for every student, it is mandatory to clear these 2 4-credit courses. One is on professional ethics and human values. No student gets degree unless he or she has passed in this 4-credit course. Similarly, another course is on energy and environment studies. Unless a student has passed this course, this is also a 4-credit course, degree is not awarded. Intention is to ensure that we sensitize students about human values as well as the environment, our surroundings. We have also been working with Rotary Club and have established a Rotaract Club in the university so that students are exposed to selfless social service. Similarly, we have established one Cancer Foundation, chapter of the Cancer Foundation on the campus so that students get the opportunity to work for such patients. We have also adopted 9 villages around our campus to take care of the community. Our faculty and students have been visiting these villages to educate the poor people. One example I can give, textile technology is the discipline which only our university has in the whole of Madhya Pradesh. In Madhya Pradesh, university and before university, the engineering college was the only institution, and even today it is the only institution offering BTech, MTech, and PhD program in textile technology. Every year, 1 month free training is organized for the women living in these villages, free of charge. And in now last so many years, some of them have become entrepreneurs in their own village. So they are given training on cutting, designing, sewing, and so on. Besides this, we always believed that students would start inculcating the values and also learn more significantly if they are given an opportunity to interact with the people who have significantly contributed to the science and technology and also to the society in totality. So right from the beginning, we established various orations. Like today we have C.V. Raman Memorial Oration. We also have Aryabhat Memorial Oration and so on. Intention was to give message to the students that it is not only those who are living in United States and other countries who have been contributing. This country, great country, has also given birth, it has also produced great scientists, philosophers, and other and thinkers in other disciplines. So far, more than 30 Padma awardees have visited our institution till last year, that is pre-COVID, and in last 1 year we have not stopped. Such visits have continued, but of course now it is digitally. Intention is to inspire the students so that they can see those people who have made great contributions. When Anil Kakodkar speaks about his experience of Pokhran, students start believing. So it is more effective than simply reading from books. They will listen to Madam Rohini Godbole. The learning will be more effective than simply reading from books. With this spirit, we have been inviting people who have made great contributions, who have proved to be great sons and daughters of this great nation, not only restricting to science and technology, but from various spheres of life. I am very much confident that our students have a great learning opportunity today to listen to Madam Rohini Godboleji and not standing for a long time. Being a teacher, I have a tendency to keep on and on. Therefore, I need to stop here and once again welcome Madam Godbole to this webinar. Thank you very much.
Thank you.
Thank you very much, sir, to express our affection and reverence to one and all present over here. Now I invite Honorable Chancellor Shri Vaishnav Vidyapit Vishwavidyalay, Shri Purushottam Das Ji Pasari, to address the August gathering. Over to Chancellor, sir, please.
Namaskar, Honorable Chief Guest and distinguished speaker of the third C.V. Raman Memorial Oration, Padma Shri Dr. Rohini M. Godbole, eminent physicist and honorary professor, Indian Institute of Science, Bangalore, Honorable Vice Chancellor Shri Vaishnav Vidyapit Vishwavidyalay, Dr. Upinder Dhar, Honorary Secretary Shri Vaishnav Vidyapit Trust, Shri Kamal Nayanji Bhuraria, Coordinator Science Club, Dr. Nitin Kataria, HOIs, HODs, all the distinguished participants who are present with us through this online platform, and my dear students. First of all, I would like to give my heartiest congratulations to Madam Padma Shri Dr. Rohini M. Godbole for having honored with distinguished Padma Shri Award in the field of particle physics as first woman physicist in the country. Madam also recognized by the French government with order National du Merit for her role in collaboration between India and France and her dedication to promoting women in science in January 2021. I welcome on this occasion, Madam. The Vaishnav Shaikshanik and Paramarthik Nyas of Indore is a well-known charitable organization in the country, known for its services and activities for the social upliftment of the people of all classes and walks of the life. It was 137 years back in 1884 under the patronage of enterprising merchant of cloth market of Indore that Sri Vaishnav Sahayak Kapra Market Committee was established, realizing that education is essential for rapid growth of the society and leading a happy life. Presently, 25 educational and social organizations with more than 21,000 students are functioning under the aegis of Sri Vaishnav Trust. Sri Vaishnav Vidyapit Vishwavidyalaya was established by Gazette notification of the state of Madhya Pradesh on 8th January 2015. I appreciate the efforts of the university to organize the series of memorial oration in the memory of great Indian scientists such as Aryabhat, Srinivas Ramanujam, Sri C.V. Raman, and Vikram Sarabhai. In my view, these orations work in two ways. Firstly, they draw attention of younger generation to the contribution made by the scientists of Indian origin. Secondly, these orations give opportunity to our students and faculty to interact with the well-known scientists and scholars of our times. I have a strong belief that in line with previous oration, the third oration to be delivered by Madam Godbole today will be a great learning for all those who are present in this webinar. Thank you. Jai Hind.
Thank you very much, sir. Now I request our head of the department physics, Professor Uttam Sharma sir, for the citation of Padma Shri Dr. Rohini M. Godbole ma'am. Over to Sharma sir.
It's a matter of great privilege for me to read the citation for Padma Shri Dr. Rohini M. Godbole. I quote, Dr. Rohini M. Godbole is one of the most prominent and internationally renowned theoretical particle physicists of India. Dr. Godbole did her MSc from IIT Bombay and PhD from State University of New York at Stony Brook, United States, and was later conferred D.Litt by SNDT Women University, Mumbai. Dr. Godbole started her career from Tata Institute of Fundamental Research and served in many leading organizations in India and abroad. Dr. Godbole is currently honorary professor at the Center for High Energy Particle, Indian Institute of Science, Bangalore. Dr. Godbole worked extensively on different aspects of particle physics phenomenally over the past 3 decades. She has authored more than 300 research publications in referred journals and having 15,000 plus citations. Her work on high energy photons formed the basis from the next generation of particle collider used to study the fabric and composition of the universe. One of the analyses suggested by her to probe physics behind the standard model using properties of the recently found Higgs boson has been used as a reference for the experiment at the Large Hadron Collider. Apart from her work in science, Dr. Godbole is also a much sought after communicator of science. She has authored many books for inspiring girls. The book Lilavati's Daughter, the Woman Scientist of India, edited by her along with Professor Ramaswamy, was published by Indian Academy of Sciences in the year 2008. She is a member of Association of Academics and Society of Science in Asia, Committee on Women in Science, and Inter-Academy Panel for Women in Science. Dr. Godbole, Fellow of all the three sciences, Academy of India, is also a Fellow of World Academy of Sciences and a founder chair of Panel for Women in Science of the Indian Academy of Science. Has many Dr. Godbole has many awards to her credit. Devi Award, Satyendranath Bose Medal, Rustam Chokshi Award, Meghnad Shah Medal, R.D. Birla Award are few of them. She is the recipient of Padma Shri conferred by Government of India in the year 2019. Government of France honored Dr. Godbole with Order National du Merit, one of the highest prestigious French civilian award, while making a reference to her internationally acclaimed contribution to particle physics and having successfully set up the strong and highly appreciated scientific collaboration between France and India. Shri Vaishnav Vidyapit Vishwavidyalaya takes immense pride in honoring Padma Shri Dr. Rohini M. Godbole by inviting her to deliver the prestigious third C.V. Raman Memorial Oration on 27 February 2021 at our university campus. Unquote.
Thank you, sir. I request technical team to present the citation virtually to Dr. Godbole ma'am on behalf of Honorable Chancellor Shri Purushottam Das Ji Pasari and Vice Chancellor SVV Dr. Upinder Dhar. Thank you, sir. Now, not taking much time, I request our chief guest, Dr. Rohini Godbole ma'am, to please deliver our most awaited third Sir C.V. Raman Memorial Oration on shedding light on the dark matter in the universe. I request the audience to please put their questions in the chat box for question and answer session after the oration. Ma'am, please share your screen.
Thank you very much. I will share my screen in a minute. So the Chancellor of the DVB University, Purushottam Dasji, Vice Chancellor Upinder Dharji, and Neetu, with whom I have been talking for the past month and a half about this oration, and all the others, particularly also the students and the faculty who are there as attending this talk. I give you all my very best wishes for the Science Day, which we all want to celebrate by realizing the importance that science has for our lives. And I'm very happy to hear all the various, uh, how should I say, the method, the schemes and ideas that your university actually practices, particularly the two courses that Upinderji you mentioned about the compulsory 8 credit courses for the students. I really feel very happy about the fact that the students go out to the university learning about ethics and as well as the raging problem of the most important problem, I think, of environment. So I congratulate the Vidyalaya for doing such forward-looking, taking such forward-looking steps. And now I will take a moment and share my screen, and I will talk about the announced title, that is the dark matter in the universe, and try to shed some light on the idea. So just bear with me till I share my screen. 1 second. Yeah, share screen. Okay. Can people see my screen well enough?
Yes.
Okay, good.
Yes,
Thank
madam.
you very much. So now we will try to begin, so to say, at the beginning. So what I want to tell you today is something that I have been working for the last, some aspects of my own work. It touches on my own work for the last, that I have been doing for the last 10 years or so. So, but of course, that's not the only reason for choosing it. I will explain to you why I decided to talk about dark matter in the universe. And I will try to, therefore, the plan of the lecture is to begin with to tell you what is dark matter. And then I would try to argue why this is the next frontier to cross for theoretical physicists. And then I will go to the third question as to how does one hunt for this dark matter. As the name dark suggests, and as we will see, this is a matter we cannot see. So how do you hunt for things that you cannot see? And then what can one do in the experiments at the Large Hadron Collider? And this last point is where I will touch upon some of my own work. So the accepted worldview in the world of particle physics is that the world, everything around us, everything in the universe is made up of some fundamental building blocks. And those fundamental building blocks, we call them quarks and leptons. And these are just names, and we are not going to need this much further. So right now, just take them as these names. And what is more important is that these fundamental particles are held together to make everything around us by fundamental forces. Forces are also fundamental. Every force can be understood in terms of 4 fundamental elemental forces. And further, these fundamental elemental forces are also carried by fundamental particles. And the names of those fundamental particles are the photon, the W and the Z boson, the gluons, and the omnipresent Higgs boson, about which we have read in the newspapers, God knows, for last 10 years. So what happens is that quarks make protons and neutrons. Protons and neutrons make nuclei. Nuclei plus electrons make atoms. Atoms make molecules. And molecules make everything that's around us. So this is the accepted worldview. And this is what particle physicists have arrived at in the last roughly 100 years. The first elementary particle was electron, to be found by J.J. Thomson in 1897, more or less similar to the time scale at which your trust was set up. So this is a story of 1.5 decades almost. And what is very interesting, till now you would say, okay, so this is a matter of interest to maybe 10,000 particle physicists in the world. Why should I be worried about it? Apart from just the intellectual happiness that all of us, mere human beings staying on this earth, are able to comprehend the ultimate workings of everything around us, this itself is an intellectual achievement. But apart from that, there is something even more important. And that has to do with the fact that the laws of particle physics, which we have found to be functioning at the inside atoms and nuclei, are seem to be of relevance, seem to be functioning, not only just functioning, but also seem to be important to address and understand things that happen on cosmological time scale. Now, what is meant by cosmological time scale? What is meant by cosmological time scale is to what happened at the beginning of the universe, or what is happening at astronomical distance scales. Now, what are the astronomical distance scales? They are millions of megaparsecs. And what is one parsec? One parsec is 3.2 light years roughly. That means it's the distance that light travels in 3.3 years. And imagine light from sun reaches us only in 8 minutes. So that should give you the idea what one parsec is all about. And what happens is that things that happened on those cosmological timescales, or which are happening even today at the astronomical distance scales. And we have asked different questions. Physicists, astrophysicists have asked these questions, and we have been able to answer them as to how was everything formed? How did the nucleons form? Can we explain the relative abundance of relative elements in the whole universe? And all these questions are understood in terms of astrophysics, physics, some known classical physics, but equally important, we need to know the laws of particle physics that we have found out by studying the interior of matter at the lowest distance scale. So that is why particle physics is not for particle physicists alone. Particle physics plays a fundamental role in our understanding how the universe began and how the universe has developed and how are we ourselves formed. I mean, all of you would agree that these are extremely fundamental and at the same time very interesting questions. And today we actually know that all the fundamental laws of motion are contained in this one equation, which can be actually printed on the back of a t-shirt or a jacket, which you can buy in the biggest laboratory, particle physics laboratory in the world, called CERN in Geneva. But you don't need to know what these symbols mean. This is just to tell you that the achievement of the last 1.5 century of the particle physicists. So now, for this whole thing to be true, to be proven, to be correct, that this indeed describes the laws that dictate interactions among these fundamental constituents, we needed to find the Higgs boson. And stakes were extremely high. And the Large Hadron Collider was built for this, to look for the spin zero Higgs boson particle. And lo and behold, it was found on 4th of July, 2012. And right now, I'm actually showing you a picture, the first event that was shown by CERN in the talk, which I was actually present, announcing the discovery of the Higgs boson. And it was a reconstruction of that event. And I'm showing you the reconstruction of that event done by the detector called CMS, and that I compact muon collider. And I'm choosing that because this is the detector in which the Indian experimentalists participated. Our Indian groups experimental groups have participated in this. So this is really the terminus for the train for what we call the standard model of particle physics, which is described by these equations. Okay. And this is a cartoon which I like very much, which says, this is a cartoon from CERN, which is LHC, and this the scientist, she is coming and saying, we found what nothingness is made up of, what vacuum is made up of. And then this other, her friend says, yes, it's quite something. I'm just trying to show you the impact and the importance of this fundamental discovery. And then, natural question that anybody would ask, is the journey of particle physics now over? We have gone from molecules to atoms to nuclei to inside the nuclei. And now I have told you that the journey is over. We have opened the Russian doll and we have gone inside. We have opened the innermost layer. So now, are you now finished? This is a question that anybody can ask particle physicists. And the answer is actually no. And the answer is no, not because we particle physicists like to keep ourselves occupied, but it is because, as I told you, there are connections between the laws of particle physics and what happened in the early universe, or what is happening in the cosmos right now. And there are many cosmological observations which lack an understanding, either lack an understanding or we do not have a complete quantitative understanding using just the laws of standard model. And because the laws of standard model are relevant to what happened in the early universe, to what is happening today in the universe, the fact that they cannot be explained in terms of the standard model alone means that there is something beyond the standard model. There are some forces, some particles which go beyond, and it is the sort of this, the quest for this beyond is really what keeps particle physicists still focused on that aim. And there are three separate issues. One is, and this is the topic of this oration, and that's actually the most important one according to me, and that is the dark matter in the universe. We seem to find a lot of matter in the universe that does not shine. And, we see stars, we see planets, but we see a lot of things. And how do we then understand that it exists? I'm going to explain that to you in a few minutes. Secondly, our universe seems to contain only matter. Entire universe, as far as you go, you find only matter. We do not find antimatter. Even though at the beginning of the universe, from our understanding today, which has been sort of tested by experiments, at the beginning, there was equal amount of matter and antimatter. But in today's universe, we have complete dominance of matter. And last but not the least, the third puzzle is that the universe seems to be accelerating. And it is these three very important puzzles that cannot be right now understood in terms of the accepted theory of particle physics. And therefore, we would like to study further and try to get answers as to how these puzzles can be explained. I talked about this dark matter story again earlier already, but just to tell you that this is the discovery that won the physics Nobel very recently. Then the cosmic acceleration, that is the universe seemed to be accelerating, the discovery has won the physics Nobel in 2011. Then there are a few other things that are not among these cosmic puzzles, but which are puzzles to particle physicists. And one has to do with the fact that we do not understand why neutrinos have non-zero masses. And that is what got the Physics Nobel Prize in 2015. And last but not the least, we have found a Higgs boson at the Large Hadron Collider, but which seems to have mass which is comparable to the masses of the other heavy particles in the standard model. And this got the Nobel Prize in 2013. So these two are more the puzzles of the particle theorists who are trying to understand something at the sort of something at a conceptual level. But these three, I would say, are the observational level problems. And physics, after all, or any science, after all, we are the aim of science is to understand the observations. That's how science has developed. So let's try to begin with saying, what is dark matter? So one of the contents of our periodic table of particle physics, namely the quarks, leptons, the gauge bosons that I showed you, actually they account only for the 5% of the matter in the universe. I'm going to show you the evidence in half a second. So here, only 5% of the total matter in the universe is made up of quarks and leptons. Whereas 27% of the matter in the universe, we don't even know what it is made up of. And 70%, almost 69% energy of the universe is not even matter. It's just pure energy. And we really don't have understanding of these three issues. And we are able to do this, reach this conclusion that the baryonic matter forms only 5% of the total matter in the universe, for the simple reason that we have understood the interaction of all the standard matter particles completely. So let us understand how we have reached at this conclusion that there is dark matter in the universe, which is not contained in our list of standard model particles, which we have painstakingly established over the last 150 years, and which have, by the way, let me tell you that the discoveries related to the standard model have won about, I think, 36 or 37 Nobel Prizes since the beginning of the Nobel Prize Awards in physics. So this is indeed a very important achievement. And in spite of this important achievement, there is something that we simply don't understand what it is made up of. This astrophysical evidence of dark matter started from a very famous astrophysicist called Zwicky. What Zwicky found out, that when he was trying to measure, there are galaxies have stars, and the stars rotate. They rotate about the galactic center. And what he noticed, that if you measure the speed at which a galaxy is rotating, then if this mass, if you look at the mass that the star is rotating with, if that mass has to rotate at that velocity and still be held in orbit, such that the kinetic energy doesn't take it out of the galaxy completely, to do that, there has to be much more than the visible mass in the galaxy, so as to hold it together inside the galaxy. So it's like saying that the pull of gravitation of the extra mass, because they could always compute how much was the mass that was seen inside the galaxy, and since the speeds at which the stars were rotating was much faster, that if there was no other mass inside the galaxy, the stars should have been gone out of the galaxy. It's like you take the piece of thread and you tie a stone and you start moving it. If you move it very, very fast, such that the tension in the thread is not able to hold that stone, the stone will fly away. So the fact that the stone doesn't fly away means that I am providing enough tension in my thread, and that is indeed, that tension was being provided by the additional gravitational force that is extended by a mass that we cannot see, but it must be there because the stars are held in orbit. This was the first observation by Zwicky, but a very famous astrophysicist observer called Vera Rubin actually set it on very, very firm footing. With this microscope, she actually measured spectrographs of light coming from a large number of stars, and this was painstaking work, took about a decade. And what she found out was the following, that if the visible mass in the galaxies was all that there was, then the velocities of rotation of the stars inside the galaxy should have decreased like this as you went away, further and further away from the center of the galaxy. But what Vera Rubin established is that the velocity of the stars as you go away and away from the center of the galaxy does not decrease, but actually remains constant. Now let's understand what does that mean a little more carefully. So what she measured this, did these measurements very accurately for something called spiral galaxies. A spiral galaxy looks like this. I wish I could have shown you. You can go. I will leave these slides with your institute, and you can go and look at this thing on the YouTube, where you will see actually a picture of a spiral galaxy and the various stars in that spiral galaxy rotating around the center. So now if stars rotate, that you can see. Now what happens is that normally you expect stars closer to the center to rotate faster. That's a very simple formula, and the only formula I'm going to use in this talk. So those of you who have learned some mechanics and learned about centrifugal motions, circular motions of body around the center, you can derive this formula very simply, that the velocity of rotation of an object around this center is given by this simple formula, where the g is the Newton's constant, m is the total mass enclosed inside the orbit of the object, and r is the radius of the object. So if there is a star f at a distance called rf, and if there is a star n at a distance called rn, and if rf happens to be 2 times rn, then you can just use this formula and you will realize that if rf is 4 times rn, then f should rotate twice as slower. And reality is different, as I told you already, and I will show you in the next slide the measurements. So the fact that the stars which are further away, we realize that should actually rotate slower. But what we find in all the measurements, that all the stars in the spiral galaxy, as you go away and away from the center of the galaxy, the velocity seems to be, if anything, rising very slightly, but more or less in the measure of this thing, the error of measurements, it's actually almost constant. And the difference between what should have been and what is observed is absolutely huge. And this is the evidence that there is more matter in the galaxy than we can see, that is visible, and that is the dark matter, a matter which does not shine. That is the point. That is one of the first and very well established evidence for dark matter. But we don't have to depend only on that. What happens is that there is something called gravitational lensing. I think some of you would have learned that when there is very heavy object, even light curves around very heavy objects. Normally light travels in a straight line, but because of a heavy object, the gravitational attraction actually makes the light curve, and as a result of which you can actually map the sky using photons, which actually change by small deviations in the path of the photons that reach us, and that is called gravitational lensing. So big bodies which have a lot of gravitational attraction actually serve as a lens, like an ordinary optical lens changes the path of the light. And here these are there are two galaxies which are colliding, and these two galaxies have been photographed in the X-rays. The red is the region where when you photographed the collision exactly at the same time, once in the X-rays and once through the gravitational lensing. And what they see is that X-rays show you the red image, and the gravitational lensing shows you this blue image. What that means again is that there is more mass that you cannot see, because X-rays are something that you can interact with light. So there is a dark matter which does not produce any X-rays, but it produces gravitational attraction, and hence it is seen in a picture of this collision using gravitational lensing. And last, so this is at the distance scales of galaxy clusters. This is at the distance scale of single galaxy, and this is at the distance scale of the universe. This comes from what is called the cosmic microwave background radiation, and this is the universe as it was seen a few minutes after the Big Bang, after the production. And these measurements themselves got a Nobel Prize, in fact, some time back. And what you find is that this temperature, according to the theory, should be completely uniform, and the small uniformities indicate the existence of early nucleation centers, which then allowed galaxies to form. And this existence of such small variations, because what this is a map of temperature difference or temperature fluctuation from the average temperature of the entire universe 3 minutes after the universe was formed. And the fact that it is not completely uniform, the non-uniformities track the places which provided the potential well or the nucleation center. Like for a crystal, we get a nucleation center, the nucleation center for the formation of the galaxies. And from seeing today what the galaxies are, we can actually project backwards using our calculations and see what should be the anisotropies, and they match with this anisotropies that the Planck experiment, it's a satellite experiment, has measured. And this too requires the dark matter, because dark matter provides the potential well where a remaining matter starts falling, and that's how initial stars and galaxies get seeded. So therefore, what we have seen is that there is dark matter and the galaxies, there is dark matter in the galaxy clusters, and there is dark matter in the scale of the visible universe. So therefore, there is very strong astrophysical evidence that dark matter exists inside the solar system, at the kiloparsec level inside the galaxies, at the megaparsec levels in the clusters of galaxies, and at the gigaparsec level at the beginning of the universe. People have been able to measure what, of course, because that's what they measured, what are the velocities of this dark matter. And they are able to show that today the dark matter velocities are about 200 kilometers per second. So this is a measurement. So this is all that we know about dark matter. We know it exists at all scales in the universe. We know it does not shine. We know it has gravitational interactions, because that is how we have learned its existence. And we know that it moves at a very small speed at 200 kilometers per second. So what I can now conclude is that astrophysical evidence is extremely strong. And we know that there are relics which are left over from the big early universe, which are these dark matter particles. And what we have directly experimental evidence is only for their gravitational interactions. But the point is that if they exist in today's universe, and we can actually try to calculate from the theoretical understanding of the early universe what should be the density today of these relic particles. And those calculations actually depend on how the early universe evolved and what was the particle content of the particles in the early universe and in their interactions. And in that understanding, we realize that the dark matter particles must have interactions other than the gravitational interaction. So this is something that we have understood only because we have understood how the universe behaved, how the universe evolved in the initial stages. But to be honest, if you were to ask us, the physicists and the astrophysicists, do you have any observational information about the mass of a single dark matter particle? Observations cannot tell us. Observations can only tell us the amount of dark matter. Observations can only tell us, because they can only tell us the required gravitational force that is required to explain this or to explain this or to explain this. Okay. So observationally, we know it has gravitational interactions. Our theory of early universe says that they must have some more interactions, and we have no idea what the mass should be. But because I already tried to explain to you, not very clearly, but as I said, dark matter has implications for the formation of the universe, and therefore, what is observed in the cosmic microwave background radiation has implications for dark matter mass. And what the cosmic microwave background radiations, which are these measurements of anisotropy in the cosmic microwave background radiation, these actually tell us that the dark matter is a particle which will go out of thermal equilibrium with radiation in the early universe when it is not moving at relativistic speeds, because it has to stay with matter, it has to provide that potential veil. And that is why neutrinos, which we know are very small mass particles, cannot be the dark matter, even if these neutrinos satisfy the other property, namely they do not have charge, electromagnetic charge, and therefore they will not shine. So this heavier dark matter candidate is usually called cold dark matter. And this principle of weakly interacting massive particle as a dark matter particle has been reigning for a long time, but we have still not been able to find it. So let's move on to that next. So if you ask a particle physicist, the particle physicist will say that the dark matter particle we think should lie somewhere in this. This is a meter streak of mass, and the mass is measured or mentioned in a very strange unit called electron volt or giga electron volt. Many of you will know electron volt as the energy that an electron gains when it falls to a potential difference of 1 volt. And giga electron volts means 10 to the 6 electron volts. And why am I giving masses in units of GeV? Because of Einstein's relation, which says that E is equal to mc square. So when I say that the mass is, for example, 1 GeV, what it means is that the mass times c square is 1 GeV. Okay, so instead of writing all the time mass by c square, I call it mass in GeV units. And particle physicists like to think that a dark matter particle is perhaps in this mass range between 10 to the 0, that is 1 GeV, to about 100 GeV. This is really the region that particle physicists had favored and the cosmologists for a very, very long time. But we cannot rule out a dark matter being a particle in all these other mass ranges. I'm not going to discuss all that. I'm going to stick to our current hypothesis that dark matter is perhaps a particle in the mass range between maybe not even 10 to the 1, maybe 1 GeV to hundreds of GeV. And I'm going to discuss that further. So what happens? What is the thing that we do know about dark matter? So what we do know from the measurements of the dark matter density, that the dark matter density today is indeed, it's given in certain units, which you need not go into, but in certain units, this is a number 0.120 plus minus 0.001 has been measured very accurately. That's all I want to tell you. Now I take a particle physics model. I can calculate what the Rayleigh density should be. It again depends on the theory, which again we do not want to go through. But just see that this is the measured number. And this is a number that my model computes, that in a given model of interactions of the dark matter particle, you can compute what this number ought to be. And that number is given by 3 into 10 to the minus 27 centimeter square per second divided by the averaged annihilation cross section of the dark matter times the velocity of the dark matter particle. This is a theoretical construct. We compute this, and now you say that if the now you say, therefore, if this is the measured quantity, then the average annihilation cross section in my model should be given by such that this equation will be equal to 0.120 plus minus 0.001. So the couplings of the dark matter particle with all the other standard model particles will decide this annihilation cross section, sigma annihilation, and therefore the relic density that is predicted in the model will depend on the sigma annihilation cross section. Hence, it will depend on the interactions of the dark matter particle that exists in my model, and the combinations of this coupling and a mass of the dark matter particle m quite twiddle will actually can produce the right relic. So the particle physics model controls this sigma annihilation. So therefore, what we do is that we take a particular particle physics model, and we know the particle physics model has a prediction for sigma annihilation. Then we calculate the prediction in that particle physics model for the relic density, and then we check it against these measurements. And these measurements that have come from Planck, they have come from these measurements of anisotropy. All right, so this is how the story goes. And that's one of the ways in which you can try to constrain theoretically the model. And so you basically, if your model does not produce the right relic density, because this has been observed, you will throw that model out of the window. But now, supposing you have some models which actually do explain the dark matter, do produce, they have in the calculations do produce right relic dark matter density that has been measured by Planck collaboration. Then you ask, how are you going to measure? How are you going to detect this dark matter? It's dark. How are you going to see it? So actually there are different ways, and I'm going to go through some of them, and I will only introduce words here. One is called direct detection, where the dark matter particles, you keep a detector way underground, and the dark matter particle comes and hits the heavy nucleus contained inside this detector. This is the detector, and you measure the recoil velocity of the nucleus that the dark matter particle would have hit. And by measuring the velocity of the stuck particle, you try to reconstruct whether, try to see what was the mass of the dark matter particle. So this is like, you take a billiard. I'm sure many of you have looked at billiard ball or snooker match. You take a little big pole and you move the particle. And by looking at the way the particle struck billiard ball moves, you can figure out which was the direction by which it was pushed in. So this is a bit like that. The second one is that at the colliders, you actually produce the dark matter particles. And this I'm going to discuss at the end of my talk. And then there are indirect detections. And these are detections by experiments which are based on space-based experiments, sitting on satellites. And what you do is that since dark matter exists everywhere around us, in space too, dark matter particles annihilate, and the annihilation actually produces visible particles like electrons, like photons, like X-rays. And these detectors try to detect those X-rays, try to detect those electrons, muons, and from that, they try to figure out whether a collision like that annihilation event happened. Then there are also some other experiments called ice cube neutrino experiments. So there are different ways in which people try to detect these dark matter candidates. As I said, how can we detect it on Earth? I'm not going to talk too much about space-based detections. How can we detect it on Earth? This I explained to you, that you hit a big chunk of water or a heavy nucleus of xenon, and then you look at the guy comes from outside, the WIMP, the dark matter particle, and it hits this nucleus, and you can measure is the recoil energy of the nucleus, because the dark matter particle has no electromagnetic interactions. You cannot detect it anyway. So indirectly, through the motion of this nucleus, you try to measure, you try to figure out whether a dark matter particle has actually passed through. And that is how you make big measurements. And unfortunately, over the past 20 years, such measurements have been done time and again, and no evidence for such event has been seen. So that means that you rule out a certain region in the WIMP nucleon cross section versus WIMP mass plane. So all these latest measurements have now told is that we have not seen a dark matter particle in the mass range between 10 GeV to 100 GeV, okay, 2 GeV to 100 GeV, which has a, if it exists, its cross section has to be less than this particular number. That is all that we have learned so far. So again, here more pictorially I show you. You can, in the direct detection, the dark matter particles annihilate and produce standard model particles. This is done by experiments that are sitting in space. Indirect detection is this one that I indicated to you, that a dark matter particle comes and scatters off a standard model particle, and the standard model particle moves away, and you measure the relative velocity, the recoil motion of the xenon nucleus, and that's how you try to detect this indirectly. And at a collider, you try to make it in the collisions of standard model particles, which will produce for you a pair of dark matter particles. And these are the three different ways. And so far, we haven't seen any evidence for the dark matter in any of these three processes. And a result of which, the evidence of dark matter, it's been ruled out in certain regions of parameter space, that is the mass space, and the space of the coupling, that is the cross section. And therefore, the job of finding this dark matter is actually becoming one of the raging problems. And since Large Hadron Collider is something that we have made, a machine which exists since the discovery of the Higgs, that is in 2013, if you just look at the number of papers people are writing on how LHC can look for dark matter, the number of papers looking for dark matter at the LHC has been increasing very fast for the last few years, and it's increased even more. So this is this huge parameter space of dark matter candidate. This is the same picture I showed you on the meter stick. But again, as I told you, in the framework of a model, we expect the dark matter particle somewhere here in this mass range from 10 to the 1 to 10 to the 100 GeV, and that is the mass range that we would like to look at the Large Hadron Collider. And more importantly, when we actually designed the Large Hadron Collider, it was designed to find the Higgs boson, but we had also hoped that it will provide us answers to the question of what the dark matter is, why there is matter-antimatter universe in asymmetry in the universe. Now that we have found the Higgs, and this physicist has reached and climbed the peak of the Higgs boson, one has realized that the peaks of the dark matter or peaks of the baryon asymmetry of the universe are still further away and are still bigger peaks, still taller peaks. And these are the peaks that we are trying to reach. So this dark matter search at the Large Hadron Collider, therefore, it's one of the burning problems of particle physics. So, before the Higgs discovery, there were a whole landscape of all kinds of theories beyond standard model. Just the discovery of the Higgs removed actually a whole lot of theories as not being correct. But now we want to use dark matter at the LHC to probe this landscape of physics beyond standard model even further. And we want to use the Higgses for that. Just to give you an idea, the Large Hadron Collider has so far produced about 7 million Higgs particles. Not all these 7 million Higgs particles can be detected, but this tells us that now, after detecting the Higgs boson in 2012, the LHC, the studies of at the Large Hadron Collider, now has turned towards rare decays of the Higgs bosons. And now the question that we are all looking at is that, are there any additional exotic decays of the Higgs which will into the dark matter particles? Again, if it's Higgs decays into dark matter particles, then the detector cannot see such a decay. Such a Higgs cannot be seen by the various methods that the Large Hadron Collider employs to see the Higgs boson. And the question is, how do you look for such an invisible decay of the Higgs? And these decays can actually exist in something called supersymmetric theories. These are actually theories that people had postulated to explain one of the puzzles to the theoretical puzzles that I listed to you in my first few transparencies. And that is the puzzle why the Higgs boson has the same mass, similar mass as the W and the Z boson. Technically, we call it what keeps the Higgs boson light. And there is this theory and phenomenology of supersymmetric particles. This is something, a book which we wrote around 2005, and that is how to look for the supersymmetry at the Large Hadron Collider. So far, we haven't found any evidence for supersymmetric particles at the Large Hadron Collider, but these supersymmetric theories have a ready-made dark matter candidate. And therefore, now our question is, can we look for supersymmetry through the dark matter at the Large Hadron Collider? And that is what I have been doing. And this brings me to the end almost of my talk, because this is the area which I have been working for the last 10 years or so, how you can look for the supersymmetry through its dark matter candidate and through the decay of the Higgs into the dark matter candidates to an invisible decay of the Higgs. I'm going to spend 3 or 4 transparencies to give you some idea of the kind of work that goes on. I do not expect what I say from now on to be very understandable, but this is just to give you a picture of what one does in a life of a particle physicist. So what you do actually, what I have tried to convey to you is that when you have a particular model for a dark matter candidate, you can calculate the relic density. Remember, I will show you that equation once again, that in a given model, given the interactions of your dark matter candidate, you can actually calculate what the dark matter relic density should be for a given mass of the dark matter candidate. And then you can compare this with the observed relic density. So that is in the framework of a model. You can first check if your model can do that. And then you ask the question, can this now dark matter density parameter space where you produce the right amount of relic density, can you use the direct detection experiments or the LHC phenomenology? And for the region of the parameter space of your model where you produce the right relic density, what are the channels through which you can look at it at the Large Hadron Collider? So the same model can be studied from 3 different windows, and that is what we do. So what you do at the LHC is you produce the dark matter in the cascade decays of supersymmetric particles, or you produce the dark matter in association with other standard model particles. Because if you produce just the dark matter particles in the Higgs decay, you're not going to be able to see it because it doesn't leave any track in the detector. So what you do is that you look at processes where the pair of dark matter particle is produced in association with another particle which you can actually see in the detector. So it's like saying that, you are again always looking at things that are produced in association with something that you cannot see. But since in a big detector, energy and momentum is always conserved, you can measure this particle which was produced in association with something that you couldn't measure. And from the measurement of the momentum and the energy of the visible objects, you try to check whether there is evidence for a dark matter which has been produced in association with this particle. So this is what this is called. And this is what one tries to do. We had been working on this, and this is just to show you how on a given subject, you have to keep on working for years together. Even before the dark matter evidence was completely firmed up, even before this number 0.120 plus minus 0.001 was measured, we had still thought of how, if there is a dark matter candidate and if the Higgs decays to the dark matter, how one will look for such invisible Higgs. And this was already in 2003, even before the Higgs boson was formed. So we had suggested this in 2003. In 2013, after the discovery of the Higgs, we actually modified and made more precise predictions. And then we looked at in more recently in 2017 and 2020, as well as 2021, how now that we have seen the Higgs boson, how one can look at the collider for other manifestations, for particles which are associated in our model along with the dark matter candidate, which explains the Rayleigh density. How can one look for those particles at the collider? So these are the different kinds of things that we were doing. In this 2003 paper, we tried to say that if this invisible Higgs, this Higgs is produced in association with a Z and the Higgs decays into invisible particles, you can try to see whether a dark matter, whether Higgs has decayed into invisible particles by studying the energy distribution of the Z boson. And that is what was used by the experimentalists. And I will not go through the details how experimentalists did it, but this is what they did. And they basically, we had predicted that if you can use this process, you can try to see the Higgs in this method as long as the branching ratio, the probability that the Higgs will decay into invisible object is above 0.58. We have not seen any such event, and therefore experiments are able to put a limit and say that indeed the branching ratio of the Higgs into these invisible particles, if it exists, this should be less than 60%. Now this has continued further, and today that limit has come down to the invisible branching ratio has come down here in together to about 20%. So this is where the idea that we had suggested was actually used, and we had indeed said that you would be able to probe it if the branching ratio was up to about 0.2. And indeed, they have been able to, they have gone up to there and they have not seen any evidence. So this means that if the Higgs boson does indeed have invisible branching ratios, they are less than 0.2. And with future runs of LHC, they will be able to go further down and go down to something like, right now they have reached about 0.15. And it feels nice that idea and estimate that we had made actually agrees with an experimental result. So it's unfortunate that we haven't seen the invisible Higgs decays, but what we had said that the experiment should be able to do, the experiment has actually been able to do. But now, is that all? It is not all, because what we can do is that we can now ask the questions, what are the future experiments that are going to be able to do things? And right now, in the supersymmetric standard model, controlled by the invisible Higgs measurements, and all these parameter regions are ruled out. However, this saffron region is still something that is completely allowed by the current measurements at the LHC. And how will we probe this? We can now probe this not through the invisible decay of the Higgs, because we already reached the limit as to what we could have probed, but now we can look for the associated particles that are produced at the LHC and again probe this region. And what we have shown is that the current future runs of the Large Hadron Collider would be able to probe these points, many of them, and which are these, again, the blue points are the ones which can be already checked, and one should be able to see the signal in the upcoming runs of the Large Hadron Collider. But if we don't find it there, then we have to wait to what is called the high luminosity run of the Large Hadron Collider, which will happen 4 years from now. But what I'm trying to show you is that through this combination of different measurements, the Large Hadron Collider, the direct detection, and the invisible Higgs with measurements, we will be able to probe this particular hypothesis to its end. And if we don't find any evidence here, then we will have to conclude that the hypothesis that the dark matter is supersymmetric in nature in the framework of this particular model is ruled out. So this is what a theorist can do. This is what the theorists can point out to the experimentalist, what kind of measurements they can do to understand this reason. There are a few more technical, 2 slides of more technical information, which again, what we show is that even if we relax some of the assumptions about the early universe, because we don't know enough about the early universe, even then there will be certain regions of the parameter space which the Large Hadron Collider will be able, only the Large Hadron Collider will be able to probe, as well as the measurements of the invisible width of the Higgs decays here will be able to probe these regions. So there is a lot of hope for probing these regions, and one can talk a little bit more about this, but that's a separate talk altogether, and that's for the experts. But all I have tried to convey to you is what the dark matter is, why this issue is completely virgin, the territory is not understood, and I have given you my own perception of looking at this dark matter in the context of supersymmetric models, and I have tried to show you that the direct detection experiments, the high energy Large Hadron Collider, and any of the future planned E plus E minus colliders, all of these together can actually test the paradigm that the dark matter is the lightest supersymmetric particle in the mass range between 10 GeV and 1 GeV to about 100 GeV. And that's where I would like to stop, that the future is long, the path is not easy, but the quest continues. Thank you very much.
Thank you very much, ma'am, for your interesting and full of knowledge. Uh, I request the panelists to ask any questions, as ma'am works so much for the woman in science also. So in that area, ma'am is open to discuss with us. Any question from the panelist side?
Yeah, can I have a question?
Yes, sir, please.
Ma'am, it was very illuminating, although I'm not from physics, but I just had one layman's question. Do you find this dark matter only in the distant galaxies, or is it in our...
It's near Earth also. That is why I made a plot that even in the planetary system, we have dark matter. It is just that the amount of the dark matter around us is not very much, because we are not a very heavy body. But if you go to far away supernovae at the center of the galaxies, there is large amount of dark matter there. So the density of the dark matter near us is not very high. But otherwise, this direct detection experiments that we are talking about, they actually are looking at the dark matter which is near us, which is impinging on the Earth. So just like neutrinos impinge on the Earth all the time, this dark matter also impinges on the Earth all the time. It's just that the density of the guys near us is not so high.
So that density depends on the density of the matter in...
Yeah, to some extent. That is how, because that is actually this cosmic microwave background measurement, that the initial formation of structures of galaxies or stars happened because, like in a crystal, when a crystal forms, you have to have a nucleation center. So that nucleation center in this case is a matter of lump of dark matter, which attracts gravitationally other guys to fall into that potential well. It sits there and says, come close to me, come close to me. And that is how the structure grows. So the more massive the structure, more dark matter is around there.
Oh,
is that understandable?
Yeah.
Okay. So it's everywhere. That is actually the one point that is now here. It took 100 years for people to accept this, because Zwicky wrote his paper in 1929. So it has taken 100 years for all of us to completely accept the fact that there is dark matter in the universe. And it is this very highly precise measurements of the fact that the cosmic microwave background radiation at the time when it was decoupled from the rest of the radiation and started just evolving because of the evolution of the universe, started cooling down. At that time, if there were no structures, no dark matter, it would have been completely uniform. The fact that it is not completely uniform tells us that there was dark matter in the universe at that time. So actually a fascinating. I mean, there is a statement by Einstein which I would like to share with you. That when you think of this, you realize that it is quite incomprehensible that human intellect can understand or can comprehend what happened at the early beginning of the universe, or what is happening today at the distance scales of megaparsecs and kiloparsecs. So, it just a thought actually for me as a scientist. I find that even if I didn't do any original contribution to science, I'm lucky enough to have made a few. But even if I hadn't done that, just understanding the mysteries of universe, and that a human being, 1 meter tall human being or 2 meter tall human being, is able to comprehend and rebuild the universe in our computer, is itself very fascinating. And that's why dark matter is so fascinating.
We have been made biologically capable of that comprehension.
And that is amazing,
Yeah.
That is amazing.
Thank you, ma'am.
Thank you very much, ma'am. As you know, you are running out of time. You have some other
One question from me.
Yeah.
Again, as a layman,
Yeah.
it was very enriching oration, and we have understood many things because we are not basically from physics. I happen to be from management discipline. My question is that how are these experiments conducted? Is there a special lab required for such experiments, or they are conducted in the field?
No, that is actually a very good question, because again, what has happened, this is actually today's order of the day. Because you require huge detectors. Again, because of the question that Professor Guru Prasad had asked, that the density of these dark matters on the earth is very, very small. So you need to construct kiloton xenon in a big detector. So first, to even create that kind of xenon liquid itself costs money. So no one lab, no one country anymore can do this experiment. These are collaboration experiments. And in fact, right now, 2 big experiments are happening, one in Europe and one in the US. In India, we are trying to do a small experiment of this. I wanted to show you a picture of that. And that's happening right now in a little mine near Kolkata. But we are all hoping that these experiments will function in a Indian Neutrino Observatory when it gets built in that tunnel. India too will have a small version of that experiment. But the decisive experiments have to be huge, and decisive experiments have to be run in an international collaboration. So that's why international collaboration and the global exercise interaction is actually very important for fundamental physics nowadays.
Is that international collaboration happening? Is, say, for example, Indian Institute of Science part of this collaboration or not? It's out of it.
We don't have experimentalists who work in this particular collaboration. So in the experiments of dark matter detection, we don't have participation. But we do have participation in the experiments at the Large Hadron Collider, where you are looking for the dark matter in a collider experiment. So we do have my experimental colleagues from our department are parts of this big experiment, and that is this central compact muon solenoid detector, and that is Indian detector, and India is part of that experiment, and Indian Institute of Science is part of that group which participates at CERN. Indeed.
Thank you very much.
Very much, ma'am.
Can I ask one question? I'm also not from a physics background, having a science background. So, 2 things. In fact, one was somewhere you mentioned that the only evidence that physicists had so far was through gravitational interactions. However, some of the point you also mentioned that there are certain, properties found with photons deviating from the straight line path, following a trajectory. Could that not be used, and as a research basis to establish evidence of dark matter further?
So that was actually done. That is why I showed you that blue picture. So indeed, that is how we have measured what is the extent of dark matter in different parts of the space of the universe. This has been used actually, because that is a gravitational interaction on the effect on the photons. Okay, so you are completely right. It has been used. However, that is still the gravitational interaction of the dark matter.
Right. That's how
that is the point again and again. Okay. Right. Now we know that it must have had other interactions because of the way we understand how the early universe evolved. Because what we know is that in the early universe, there existed only radiation, only photons. Then the photons annihilated and made electron positrons. They made quarks and antiquarks. Then these quarks and antiquarks fused together and made another photon. That photon made maybe a mu plus mu minus pair. That's how the whole thing began. And in the early universe, it was like there was so much energy that the photons were creating electron positrons. Electron positrons were creating photons back again. And the whole process was happening. So if the dark matter particles were created, since we know they are created because they are here today. So that means that they have had to have interactions with the standard model particles other than the ones that we know. And we know they don't have the interactions with standard model particles because in the detections we have looked for them and we haven't found them. If they had the standard model interactions, we should have seen the dark matter particles in these big experiments. So we have this puzzle in front of us that our understanding of the early universe tells us that the dark matter must have interaction other than the gravitational interaction. But we are not it is not one of the three interactions that we know and that we have understood. So we know there exists something beyond what we have understood so far. Have I answered your question, Dr. Mandal?
Mesmerizing session, madam. It kept at least me.
Thank you very much, ma'am. And we have so many questions in the question and answers, but I know we are running out of time, ma'am.
No, Neetu, what I can suggest is that if you can share my email ID with these people. Yes, and if people send me emails, I will be happy to answer. I would have loved to stay here and answer, but as I told you, I have another Science Day talk to give in half an hour, less than half an hour.
Yeah, yes.
So I am sorry, but I will say sorry to all the students or faculty because I see many questions and some of them do have nice answers. I think they are very good questions. So I congratulate people who are asking these questions. And all I would say is that please feel free. Firstly, I think you people can actually save these questions in the chat.
Yes, ma'am.
And send them to me.
Yes, ma'am.
Give people my email ID.
Yes, ma'am.
Which is, you have my email ID. You give it to them and I will answer questions on mail.
Yeah. Thank you very much, ma'am.
Okay.
Yeah.
So my apologies that I cannot stay much.
It's,
yeah.
We are.
There is no question of apologies, madam. So this gives us an opportunity to stay in touch with you and learn more from you.
Ma'am, we have one more talk with with you all. That woman in science is pending.
Yeah.
As I told that.
I see this question by Dr. Bhavana.
Yes, ma'am.
As we know, the contribution of women in science is very less than men. Okay. I think this is a question I will answer and I will leave you people. But indeed, it's a very important question that Dr. Bhavana had asked, because this is one point that I would like to share with everybody. It is that when we talk of saying that we want to increase the proportion of women in science, that we should have more women in science, there are two reasons for this. but we think of only one reason. We think that, okay, it is important because women who want to do science should be given expression to their intelligence, to their creative abilities. But I want to say that it is not just for women. Just as science is important for women, and therefore we should increase the women's participation in science, I think women are also important to science. And that has to do with the fact that science is a creative activity, right? So what people choose to investigate, the questions people choose to ask, and the mysteries that we choose to solve can actually depend on the person's creativity, right? So firstly and foremostly, one needs to have more and more people. And since the questions we like to ask change depending on our ability as well as our social upbringing, the thinking which we have had through the times, I think it may, what kind of questions you choose to ask actually sometimes depend on who you are. And just to give you an example, I will go back quite a few decades, 100 to 1850 or 1880. I will talk about the first woman doctor, Indian woman doctor, who studied in US. Her name was Anandibai Joshi. And what did Anandibai Joshi did her thesis in? She did her thesis in gynecological problems of Hindu women. You know why she did it? Because she lost her own child at the age of 14. And when she was going to the US, she said, I want to study the gynecological problems of Hindu women because I believe that my friends, my women friends, would be much happier having a woman doctor than a man doctor. So here, directly, the kind of things she studied were decided by who she was. So this is a very simple example, but actually I can give you more complicated examples. I can give you another complicated example of our times. There is a lady called, I forget her first name. Her second name is Bulwamani. She was a person, she is a scientist working in the media lab in MIT. And what she noticed is that, you use artificial intelligence to develop algorithms for face recognition. All right. And she found that the face recognition algorithms that were developed at Google or at MIT Media Lab failed and worked only 30% of the time, only when used on African American women. When they were used on white Caucasian males, they worked perfectly. That's how they were developed. So why did they fail on African American women? Simply because artificial intelligence depends on the inputs you give them. And these people who are doing research, where white Caucasian males, didn't realize that the output is going to depend on what the input was. So if you didn't give this system an input of what a African American woman looks like, they would fail 30% of the time. Now, these are just small examples, but I can go on. And there are more intangible ways in which, I tried to give you, the last example I will end with is that, for example, seasickness. In the early time when humankind started going on the sea faring, seasickness was considered, poor sailors, they suffer from seasickness. What can we do? It's only when doctors themselves started going across on voyages and they started suffering from seasickness, they said, we must do research how to stop seasickness. So this is what tells you that what you choose to do research, the relevance of the research that you do, the choice of research that you do can depend on who you are. And that is a very simple way of saying that you need more participation by women in science. For women, of course, because those who have the creative urge, one should get full expression for their creative urge, and they should not do research simply because they are women. So that is something we have to teach ourselves, that gender has nothing to do with one's ability to do science. If some women do not want to do science and want to take care of the house, that is also completely okay. Only those who want to do it should not be held back because of their gender. So that is one aspect of having more women in science. But the other equally important part of having women in science is that it does something good to science also. Because science is always a very multidimensional space. But by adding women, or even people from marginalized parts of the society, just because people live on margins of society doesn't mean that their ideas are marginal. So inclusivity can only add more and more dimensions to science, and there are in principle no limits to what science can explore. So I hope, Dr. Bhavana, I have given you the answer as to why we need to have more women in science.
Very much, ma'am.
Okay.
Now I request Shri Kamal Narayan ji Buradia on.
Here, just a minute, I would like to share with everybody that Lilavati's daughter's book is available in our library.
Oh, I'm very thankful to you. I was going to say that I would try to send the book to your library in case it's not available.
No, it is available.
I'm glad to know that it's available.
Yeah, thank you. So readers can go through it. It's very interesting, and it is also considered as a very good contribution of Dr. Rohini.
It is also available online. I can send you the link to Dr. Neetu. But now I really must go.
Ma'am, we need your five more minutes. Just
but let us just end
for vote of thanks.
Yeah.
Yes, ma'am.
Okay.
Chief guest of the today's function, Professor Rohini Godwale ji, Honorary Professor of Indian Institute of Science, Bangalore, माननीय कुलाधिपति हमारे विश्वविद्यालय के श्री पसारी जी, श्री डॉक्टर वाइस चांसलर डॉक्टर उपेंद्र धर जी, वैष्णव विद्यापीठ के न्याय के सभी नासिकगण, सभी पदाधिकारीगण, विश्वविद्यालय के सभी निर्देशकगण, विभागाध्यक्ष, शिक्षकगण एवं हमारे प्यारे छात्र छात्राओं, 3rd CV रमन मेमोरियल ओरेशन में मुख्य अतिथि के रूप में आज हमारे बीच प्रोफेसर रोहिणी गोडवाले जी की गरिमा के उपस्थिति से हम सभी गौरवान्वित महसूस कर रहे हैं। डॉक्टर रोहिणी गोडवाले, जैसे उनका भी आपने पूरा उनका अभी और भाषण सुना, स्पीच सुना, उनका जीवन हम सबके लिए एक प्रेरणादायी पुस्तक के समान है। आज हमने उनके ज्ञान का लाभ सहज रूप से प्राप्त हुआ है। आपके बहुआयामी व्यक्तित्व से के प्रकाश में आज हम सब अभिभूत हैं। मैडम, पूरा विश्वविद्यालय, हमारा उभरता विश्वविद्यालय आपका बहुत बहुत आभारी है। लेकिन हम ये चाहेंगे कि जब ये कोविड महामारी से हम जब बच जाएं, तो आप कृपया करके हमारे विश्वविद्यालय में अवश्य पधारें। हम आपके चरण से जब आपका हमारे विश्वविद्यालय में पड़ेगा तो
आपसे मिलकर बहुत खुशी होगी, मैं जरूर आऊंगी।
निश्चय ही आज हम आपके ज्ञान एवं अनुभव से हमारा उभरता विश्वविद्यालय आज समृद्ध हुआ है। हम आपके इससे निश्चय ही हमारे रिसर्च और विजन के क्षेत्र में विस्तार होगा। मैं आज के इस गरिमामय प्रोग्राम में सभी उपस्थित फैकल्टीज, कार्यक्रम संयोजक, पूरी ऑर्गेनाइजिंग टीम एवं हमारे कुलाधिपति श्री पसारी जी, कुलपति डॉक्टर उपेंद्र धर जी एवं सभी बंधुओं का आभार व्यक्त करता हूं। मैडम, मैं पुनः आपका शुक्रिया अदा करता हूं। आप हमारे देश की बहुत बड़ी धरोहर है। आपका इकबाल और बुलंद हो। आप महिला शक्ति की प्रेरणा स्त्रोत बने। देश और दुनिया में आपका गौरव और सम्मान और बढ़े। हमारा यह उभरता विश्वविद्यालय आपके दीर्घायु एवं स्वस्थ एवं सफलतम जीवन की कामना करता है। आपका मैं बहुत पुनः आभार व्यक्त करता हूं। मैडम, आपने जो इतना समय दिया, आपके लिए उसके लिए बहुत बहुत धन्यवाद। मैं सभी उपस्थित महानुभावों का धन्यवाद देते हुए मैडम को जल्दी जाना है, मैं पुनः आपका बहुत बहुत आभार मानता हूं। मैडम, आपसे जरूर प्रत्यक्ष रूप से मिलना चाहेंगे। आशा है आप जब समय देंगी। थैंक यू वेरी मच मैडम।
बहुत बहुत धन्यवाद, शुक्रिया, बाय। नमस्कार जी।
नमस्कार मैडम।
थैंक यू वेरी मच मैम।
बाय नीतू।
थैंक यू वेरी मच।
बाय उपेंद्र जी, श्री पुरुषोत्तम जी।
Thank you, ma'am.
नमस्कार.
मैडम इसमें मेल आईडी में डाल दो वो.
Yes, sir. मैं डाल दूँगी chat पे.
मैडम का मेल आईडी डाल दो चैट बॉक्स के अंदर ताकि बच्चे सब वहां से देख सके ये क्या है.